Hey everybody, Professor Ghassemi here. Welcome back to another lecture on AI agents at MSU. Today's lecture will be talking about planning, tool use, and multi-agent collaboration, all three common design patterns when implementing AI agents. As a reminder, the theme for this lecture, just like the previous one we covered, is looking more at how we do the implementation of these three agentic design patterns. So specifically, we'll be looking at code implementations. We'll be talking about, where relevant, some of the trade-offs, highlighting recurring problems, and trying to give you intuitions for how you solve these things in practice and what to look out for in terms of pitfalls. So with that said, let's jump into the first topic, which is planning. So a planning agent takes a problem, usually a complex one, and figures out how to decompose that problem into a set of smaller, more manageable, concrete steps, okay? It does this in three sub-steps. There's generating plans given a prompt, evaluating whether that plan is going to work or not, and then, of course, executing the best possible plan. From a functional flowchart perspective, I've got it illustrated down here. We have a user. The user writes a prompt. It could be something like organize a team offsite. And this goes to an agent who first and foremost generates a plan. Now, why is organizing a team offsite a good example of where you'd want to come up with a plan? Well, because it's ill-posed. The organizing of the team offsite says what you want to do. It does not say how you want to do it. And so for any problem that's posed by a user, where the what is specified, but the how is especially vague, using planning is a really useful approach to get something valuable back to your user. It's also possible, but not illustrated here, that when you're performing planning, you might need to do check-ins with a user. I'll give you an example. Let's say we are organizing a team offsite. Okay, so at one step in this plan, we have to book a hotel room for the team, or hotel rooms for the team. And what we need to know is how many team members there are so that we book the correct number of rooms. If that information wasn't known to the agent through memories, a database it has access to, then it might have to ask the user. So there would be some step in this plan where you ask the user before proceeding forward, okay? At the end of the day, though, when you complete the plan, you're ultimately doing this so that the agent can return the output to this kind of vague or open-ended problem using the solution to the concrete sub-steps. So let's dive into a practical example of how you do this in code. And I want to note before we jump into the code examples that just like the last lecture, I'll be including every time I jump into a code example, the libraries that are used, which are reflected in the import statements here. And as a reminder, if you want to reuse any of this code on your own side, which you can do either by downloading the code in the course's GitHub repo, or you can just take an image, a screenshot of this, and throw it into GPT, and it'll turn it into actual text for you. Either way is fine. But just remember when you're doing that, I'm going to assume that you have an environmental file, that's a .env, and that you've loaded a client, in this case an OpenAI client, using that key. So just don't forget, if you're going to re-implement this code on your own side, that I assume that you've set up access and have some libraries installed that I'm showing here. So let's jump in. One common planning pattern that shows up, in fact, it's one of the most popular planning patterns that shows up, is one called React. React stands for reasoning, followed by action. If you recall our prompt engineering lecture, and actually a lot of the things we covered in the first three, React either showed up as something we discussed formally, or it showed up as a baseline that a lot of the new papers were comparing their performance against. And so what I thought would be useful is to show you an implementation of React just from scratch, which is, again, reasoning followed by planning. Now, there's a lot of code here. We're going to break it down, and you'll see it's a very simple sort of method to achieve the reasoning followed by the action. I think the right place for us to start in this code is down here, which is what we want to actually run, or what task we actually want our AI agent to accomplish. In this case, I'm a professor, so let's put something that would be relevant to me. Let's say I wanted to plan a 1-hour guest lecture on LLM agents for 30 students. Okay, well, if I want to do this, the first thing I want to do, coming up to run, just a function we call here, the first thing I want to do is specify some information that's going to go to that LLM, like we've done in the homework assignments. I need to have a system prompt, right? That's this. This is common when you're dealing with LLMs. You have a system prompt. And then I need to provide the prompt that's going to come from me, the user. That's the goal, the problem we really want to solve. And that's what shows up here in the second item of the list of JSONs. Okay, goal is exactly what comes from down here. Once I have these messages, then what I'd like to do is I'll be going through a series of reasoning followed by action steps, and I'll be doing it sequentially. So I'm going to need a for loop for that. I probably don't want to let it reason and act forever, so I want to specify the maximum number, maybe with a default of 6. And as soon as I start this process, I'm going to take whatever was in this JSON, this list of JSONs, and I'm going to pass it to my LLM client. So that's what the chat does here. Okay. Again, the chat is defined up here. It just makes a call, in this case, to GPT-4o Mini and returns the results. So the process here again is we pass in our goal, we have a system prompt, we pass that information to a language model, and then you might notice that we come here and we search through the response of the language model. This is through a regular expression for an action that was returned and an action input. In order to understand why we're searching for these two things, let's jump up here to the top and look at the system prompt together. This basically, just as you've done in your first couple homework assignments in this class, is providing some guidance to the language model about what it should return to participate effectively as a React planning agent. Okay, specifically, it's going to follow 4 steps. The first is it's going to think, so it's going to provide a thought to us in its response, and we're asking it to perform some reasoning. I acknowledge here fully that this is written in very shorthand. That's done to enable your readability. You might want to write out complete sentences rather than words like this if you're implementing this on your side. Okay, but the React planner is going to do some thinking. It's then going to take an action. Does it want to plan based on the thought that it had, or does it want to finish? So that is to say, does it want to take another step, or is it done? And then if it wants to plan, then what it needs to do, we're telling it, is also provide a concrete step. If it wants to finish, then it needs to provide a final checklist that tells us how we do this planning for the goal down here. Okay, lastly, in addition to these 3, the thought, the action input, we also wanted to provide an observation, so a reflection basically on its progress up until that point, which we're going to use to pass into the next step. So think of that as sort of like a summary of the consequences of the thought, the action, and the action input all taken together. Okay, so with the system prompt out of the way, let's jump back down here and re-review. We give a goal, we have a system prompt and the goal, we pass that to a language model. We then look at the response from the language model, and we had specified in the system prompt that it needs to give us an action and an action input. So this search helps us get the action, helps us get the action input. Some things that you might notice in this regular expression, we said above that it should respond with plan or finish up here. And so that's why we're looking for it down here. Okay, so we get this response, and what we want to do is split it, because we're extracting both the action and the action input, into the action here and the action input here. Now, if the action is planning, so if it says, I think I need to continue planning, we're not done with this task yet, then what we're going to do is take the steps, which we initialized up here as just something empty, and we're going to append what the concrete next step was. So these are the actual steps that we thought we needed to take in order to complete the task. Those steps are good for what? Well, they're good for the final checklist that we're going to print at the end. So we grab what the step was, we append it to a list. We're going to need that at the very end when we want to print. We also take the observation. This observation, if you look at the system instructions, was what happens at the end. It's the reflection on the consequences of the thought, the action, and the action input taken together. Okay? So this observation will tell the agent when it's doing the next step of its planning, for instance, what step we're on, and it will provide the steps. So that's the checklist, each of them, one by one. The message here then gets updated. And how do we update it? Well, we provide it with the text content. So that was the response that we had up here when we passed in the messages from the previous iteration. And then we're also providing this observation, which is, hey, here's what step we're on, and here's the steps so far. That's it. Okay, we run this multiple times until such point as we reach the LLM's conclusion or action, which is it outputs final or finish, and then we'll provide the final checklist. All right? So if we run that code exactly as I've shown you, we end up getting blocks of output that look something like this, where we start with a thought, we then provide an action input, and an observation. Okay? And we will continue through repeating that, again with a thought, an action input, and an observation. Why don't we go through just one set of these so that you understand the process, and then I'll leave the rest of it for you to read on your own later. So the first thought for the task that we were trying to solve, and recall, this task was planning a 1-hour guest lecture on LLM agents, 30 students, is to structure the lecture to cover the essential aspects of LLM agents, ensuring it's engaging for the students while fitting within a 1-hour time frame. So the action then that needs to be taken given this thought is to plan. We're not specific enough here to come up with the final checklist yet. So the input here will be outlining the main topics to cover in the lecture, such as what LLM agents are, their applications, and a Q&A session. And then the observation, recall, synthesizes across these to generate the steps. So those are, the outline should include introduction to LLM agents, applications of LLM agents, case studies or examples, and a Q&A session. So we've gone through this. Remember, this gets passed forward now in the code to the next step where we think again. Seeing all of this information, it says, now that the outline is in place, I need to select appropriate materials and examples to illustrate each topic effectively during the lecture. It concludes that in order to do that, it still needs to plan, and the specific action that it needs to take is to select specific case studies and resources that demonstrate real-world applications of LLM agents. Comes up with an observation, which is selected case studies to include OpenAI's ChatGPT use case in customer service, applications, and so on. But you can see here, we follow these 4 steps, thought, action input, and observation, over and over again, n times, iterating through until we arrive at a final action, which is finish, where we create the checklist that was specified in the system prompt, reviewing the lecture outline and presentation materials, confirming understanding of the case studies, and so on. Okay, that's the full React pattern. Now, as we transition from here forward, what you'll see is there's some wonderful tools and libraries that will allow you to build the React pattern, either zero or few shot, without having to write a block of code like we did here. You can instantiate this using LangChain or some other tools that exist and get access to this React pattern with just a few lines of code. Now, however, it's still important that you know how this and some of the other patterns work, because you might, especially if you're a grad student taking this class, want to come up with your own reasoning action pattern or an extension of this, which is some of what we saw in the papers we reviewed earlier in the semester. Okay, so without further ado, if the React pattern is clear, let's jump to the second topic, which is on tool use. Now, I personally think that this is the most important part of an LLM's capabilities if you want to use it in a real production setting for a real class of problems. The planning is sort of a necessary but insufficient condition for solving complex or ill-posed problems. But many times when individuals are using LLMs in practice, the language model has a predictable or finite set of tasks that it needs to solve. And each of those tasks requires the use not just of what the LLM experienced in its pre-training, but the use of a set of tools. Those could be messages from a user, those could be information that comes from the World Wide Web, something that comes from a database, and so on. So let's step through first and foremost the definition of the tool use design pattern. Make sure that we're aligned on the intuition, and then once again, we'll jump into a code example. So the tool use pattern is where an agent is interacting with external APIs, databases, etc. There's typically a few steps. You define the tools, the LLM makes a decision about which tool to use given the user's prompt. You make a call to that tool programmatically, tool returns a response, and then you process what comes out the other side. I've illustrated that here in the diagram. User makes a prompt, goes to an agent. Agent has access to a set of these tools it can call. It chooses one of them. Let's say it's memory. Memory returns the response, and then the agent can give that information back to the user. Let's jump into a code example. Again, a reminder here, you'll use the content here in the import statement to help you with defining what specifically you need to do to get the code example on the next slide working. Don't forget to instantiate your environment with your OpenAI API key if you want to run the code I'm about to show you. A couple things that I want to critically note here is we are using LangChain as we did in the previous lecture, and within LangChain there is increasingly support for the use of tools, because tool use is a common use case within the development of agents. And so they have some really useful wrappers that are built for you so that you don't have to handle the interaction with the tool, but can do it a little more naturally in a few lines of code. I'm going to be importing the Wikipedia API wrapper as well as a Python wrapper. Okay, so let's come here and look at how we can solve this in LangChain with just a few lines of code. And by solve, I mean how we can instantiate tool use for our AI agents in a very small number of lines of code. So the first thing we want to do is define what tools we're going to use. And as I implied in the previous slide through the import statements, those two tools are Python. We're going to instantiate a calculator. What specific function we're going to run. This is the one we imported. And I'm providing a description here This description is going to be useful so that when an LLM is choosing which tool to use, it can rely on the description here to help choose the tool given the prompt. So we're going to define what the tool is, how we call it, and a description that will allow an LLM to choose the right tool given the problem. The second tool that we're going to instantiate is WikiTool, which is going to make calls to Wikipedia's API through the wrapper that was kindly provided by LangChain. And this is going to allow us to search Wikipedia through an input query string. We're going to then instantiate our agent. And if you've used LangChain before, LangChain has this option to basically list a set of tools that have been defined up above here. Our Python tool, our Wiki tool, pointing to the calculator and Wikipedia respectively, are listed here. We instantiate the LLM that we're going to be using, which was defined on this slide previously. It's GPT 3.5 Turbo. And then we instantiate as well how we want the agentic model to operate. And what you'll notice here is the React pattern. So this is one of the defaults, one of the many defaults, in fact, that LangChain will allow you to instantiate. So React here is that reasoning followed by action pattern that we saw in the planning portion of the lecture. And this is a zero-shot treatment because we're not expecting any examples to be provided. So we've specified our tools, we know what the LLM is, and we have an agentic design pattern that we've specified here. We'd like it to return output so that I can print that to the screen and you can see those outputs, which is why verbose is true. Now all that's left to do is to run the agent. And to test this, I've put the following prompt. Let's figure out when Alan Turing was born and died, and then compute the difference between his birth year and the year he died. So why did I choose this? Because in order to figure out this first piece of information, when Alan Turing was born and died, what do I need to do? I need to call Wikipedia to get that information. And then what I need to do is go to the calculator and take the difference between the year of his death and the year that he was born. So I'm going to have to call both tools. And what I would like my React planner, the reasoning followed by action planner, to do is understand that I need to call the Wikipedia tool in the first step, and I need to call the Python tool in the second step. Let's look at what the output here looks like. So it starts with a thought, very similar to our cute custom build of the React planner in the planning section of this lecture. It says, I can use Wikipedia to find Alan Turing's birth and death, then use a calculator to find the difference between the years. So it starts with an action, Wikipedia, and then it provides an action input, Alan Turing. Okay, an observation is output, just like we had in the code example we did from scratch together. The page is Alan Turing. The summary is Alan Turing, and then it provides, it looks like his date of birth and death, was an English mathematician, a computer scientist, etc. So notice here that the pattern that's output by the React agent is exactly what we saw in the planning lecture. There is some thinking, the thought, there's an action input, and then there's an observation that follows from the action and action input pair. Once this is completed, the observation is made available to inform the next thought. I have Alan Turing's birth and death dates, which are clearly here, so I can calculate the difference between them and find the number of years he lived. The action in this case will be calculator, which is appropriate, and the input is going to be 1954 minus 1912. That looks right. This is just a visual indicator that Python was called to do the math. And the observation is, I now know the final answer. Okay, and it prints it to the screen. So tool use agent, that was the second topic. I really think it's super easy with the tools, and by tools I mean LangChain, to implement tool using agents today, and they're phenomenally helpful for taking your agents from just verbal reasoning based on the statistical properties of language to solving authentic problems and use cases in practice. Multi-agent collaboration is just an extension of the first two topics that we've covered in this lecture. So instead of having one agent that does some planning and has access to tools, we could have a set of agents that has access each to their individual sets of tools and does their planning process slightly differently. That is to say that multi-agent collaboration just refers to an ensemble of distinct and specialized agents. Okay, you would decompose a problem, usually, just like you would in a React pattern. You would delegate the tasks to the right agent, and then you might need to exchange some information across the agents. They might need to collaborate on some tasks, and then you synthesize the results. I'm showing you here diagrammatically what this could look like in practice. A user could communicate a need to a supervisor. This should look sort of familiar. I think in your homework, it was called an orchestrator. And then the supervisor plans out which tasks to delegate to which specialists down here. Those specialists execute, we orchestrate the responses, and then we might pass those for synthesis before ultimately giving the response back to the user. So this multi-agent system, this is what we actually built together in your first homework. I want to note here before we jump to our code example that there's more than one way to set up a multi-agent collaboration structure. There's as many ways to set that up as there are ways for human beings to collaborate. We could have a network of agents that exchange information across each other. We could have a supervisor that talks to many subordinate agents and assigns them tasks and is responsible for synthesizing results, just like your homework one. We could have a hierarchical form where you have a supervisor who has subordinate agents, which each have their own subordinate agents and so on. They could have their own tool calling or their own patterns for how they do reasoning or planning and so on. Or you could have a custom approach, right? A flat one and so on. So let's jump into the code example of multi-agent collaboration. Just as before, we've got the libraries here. We're using LangChain. And I've loaded the OpenAI API key. I've chosen GPT 3.5 Turbo as the LLM for this example. Here what I have are three steps that illustrate the entire process of building a multi-agent system. And this should be super familiar to you if you've done a version of this in the homework. We can basically start by just defining a prompt for each of the agent personas we're trying to work with. So for example, we might have a research agent persona that, given a topic, gives 3 factual bullet points about the topic. In this case, calling Wikipedia, like we did in the previous example, might be an excellent way to give some real information to help with those factual bullet points to prevent hallucination. It's not here, but that might be something we do. We might have a separate persona called an analyst, which, given the research notes, perhaps that are provided by this researcher, we want to summarize the key insight into one sentence. Okay, and then in order to run a collaboration between these two agents, in this case it's just a sequential passing from one to the other, we would take a topic. This is the input prompt. What are Alan Turing's contributions to computer science? We're first going to pass those to the researcher, who's going to provide the notes. And then those notes, as implied here, are going to go into our analyst. which is going to produce the final response. What I've done is I've provided some print statements as well as the output for you to see down here. So let's take a look at this together. It looks like the researcher does their job. They come up with a few sentences talking about Alan Turing and his importance to computer science, the role he played in breaking the German Enigma code during World War II, and so on. And then the analyst takes these 3 points that were generated by the researcher and summarizes it into a single sentence that looks across the 3 and highlights the key contributions instantiated by these 3 topics here. Okay, very simple multi-agent system. Within homework 1, I think you built something even cooler than that. So let's jump to now, to conclude this lecture, a research review. My objective here is for us to go one step beyond the very simple code examples to help you see examples of real systems that were validated through the peer review scientific publication process. These are going to be especially important if you're a person who's interested in doing research in this domain, to get a feel for what kinds of modifications, extensions, or novel takes on these agentic design patterns we've discussed so far can get you published. One of them I thought was really nice was a tool called OpenAgent, and that's what we'll be going over today to conclude the lecture. So first and foremost, what is OpenAgent? Well, it's a paper that's by Liu et al. Just this year. You can see the archive link if you'd like to read the full document, and I do strongly encourage that. The tool performs autonomous integration of GitHub tools. So what have we seen in this lecture so far? There's planning, right? We get a task. We have to think about how do we solve this task by decomposing it into subcomponents, and then we might allocate it to a special agent or a set of agents who has access to their own tools to solve the problem. That's what we saw thematically across all 3 of those agentic design patterns. Well, the issue is that when we were talking about tool use, the tools were static. Like when we looked at our very simple code example, it was Wikipedia and a calculator. The issue is going to be, if we want a real flexible agent, we want to be able to answer any question that can be thrown at this agent, maybe related to a thematic area, and so on. And so OpenAgent came up with a very clever idea of doing autonomous integration of tools that are published on GitHub, so code bases on GitHub that can help solve problems. It does this by following a lot of what we saw in the design patterns that we covered earlier in the lecture. First, it decomposes the task, but then it takes what it's decomposed and it tries to search for code repos on GitHub that can help it solve the subtasks. So it's looking for tools in the form of code repos, then sets up the environments needed to run these code repos, and then it answers the subtasks using the tools. So really, really neat stuff. Again, the main differentiator, as they show here on the diagram from their paper, is that their work is able to not just look at a fixed set of tools here, but they're able to autonomously expand the tool set and capacity to tackle any open domain task that you throw at them. It's a very neat idea. Let's go through the actual 3 phases of how their project works in practice, starting with phase 1, which is repository search. So the first thing they do is they evaluate repos for fit by looking at the READMEs. So they go to GitHub, given a user query, they make some searches, they read the READMEs, and then if they find one that looks relevant through the agent, they load those relevant repos, or they fetch new repos if they don't have any that are already loaded. This is an example from their paper of a user query. Use a GitHub repository named Sniffles to help me detect the structural variants in given gene sequences and save the structural variations in output result.vcf. This instantiates a search, in this case by name, to GitHub for a repo called Sniffles, they end up finding it, and then they can clone it and use it in the next steps. There's a second example here that's given in the context of fintech, in which case a specific name of a repo was not given. They rather described sort of a domain or topic that they were interested in. And so a search was done by topic. And there was a reasoning step over the set of options here to determine which repo would be most relevant, in this case QLib, to solving the user's query here. In the second step, they do an environmental setup. So they've identified a set of repositories. Well, the natural next step is they have to pip install all the requirements, set those up in Docker images like we're using in this class, so that they can call each of the tools using the agent and solve the problems. Okay, and so what this diagram, which is another figure that was provided in their paper, shows you is the step-by-step reasoning that they follow in order to set up the Docker image. Naturally, they start by asking if there's a Docker file in the repository, as there should be, and as there was in your homework's case. They might look and check, they find no Docker file. And then they say, well, there's no Docker file in the root directory. Let's check subdirectories. They look here. They say there's still no Docker file in the repository. So they're going to have to go and install the necessary packages that the README file stated were required, because they couldn't find that in a Docker file, and maybe there was no requirements.txt as an example. The file states that the project requires Python version 3.9 through 3.11, and they install 3.9. Okay, that gets executed. This gets passed forward, and they say, now I'm going to download the necessary data using download public data command. I'll download the data to /data. An error gets thrown. There's no such file or directory. It says, oh, it seems that the data directory does not exist. I need to create it, try to download the data again, and then it executes. What's really interesting for you to note here about this paper is the tooling that they are using is not anything you don't already have access to as a developer. So what you see Cursor or some of the other IDEs do, which is very similar to what is being shown here, there's not some super magic secret sauce that they have access to that you don't. They're using a combination of planning, action, and observation, just like we showed initially, delegation to agents with tools in order to solve a vast majority of the problems. And this is just one example of how they're doing that to set up the environment in the second step of OpenAgent. Okay, finally, the third and last phase, they've found the libraries they need to use to solve the user's query. They've set up the environments, and they have those, let's say, attached to various Docker images that they can call through API requests and so on. Well, now they just need to apply the tools. So they got to call the tool, parse the output, and see what was relevant to the user's query. What I'm showing you down here is another figure that was taken from Liu et al.'s paper, rather a sub-image of from his original figure. His original figure is much larger than this. So let's read through it together to give you an intuition for how this works. Use a GitHub repository named Sniffles to help me detect the structural variations in a given gene sequence. Save the structural variations in an output. Data of the original sequence should be downloaded using this command, ... So it comes, prior to this, there's some steps to download the data and so on, which are not relevant to the tool calling part. After it's done those preliminary steps, it comes, it runs sniffles.i, which has already been set up. It starts the analysis so that it can generate output results.vcf right here. Okay. So again, 3 phases, jumping back: a repository search, setting up the environment, and then applying the tools. It seems simple when I state it like this, right? But this work was published just this year. And I think it's a great indication that small extensions to some of the topics that we're covering in the class here today can make for really novel and valuable contributions to science and to the science of AI agents very specifically. What I'd like to show you here are the actual results of the tool that we just covered, OpenAgent, on a benchmark, OpenAct. And OpenAct, just for your reference, is a set of tasks that need domain-specific methods. Because, like, what was the motivation of doing that OpenAgent in the first place? It was that, hey, like, if you ask an LLM a complex question about finance or chemistry or some other specialty domain, it's probably going to mess up. The only way for us to trust the output that the LLM gives us is by making sure that it can call certain tools that are maybe written within code repos on GitHub that will allow it to solve the problem with fidelity. Okay, and this OpenAct benchmark is a set of 339 questions across the 7 domains that you're seeing here that test the LLM's ability to answer those tricky questions in each of these domains. So what are we looking at in this table? Here, this row, vanilla, says, if I take OpenAct and I test it, I test just regular old GPT 3.5 or regular old, in this case, GPT 4, right? GPT 3.5 or GPT 4. If I just go test that alone, how well do I do on the benchmark? Higher number is better, lower number is worse. Well, it looks like if we look at just the GPT-4 based results, if we just take a regular old vanilla GPT-4, we do okay on chemistry. We actually do quite well. A lot of these we catastrophically fail on. Visualization's okay. On average, though, look at the results. It sucks, right? 19.5 out of 100 here. If we take some of the other methods that have been published on, hey, look, that one should look familiar. React, that's the one we covered earlier in the lecture. So we take a vanilla agent, we give it a React pattern to follow. You can see that the performance goes up. It goes from 19.5 to 24.6. This is without using OpenAgent. They show a couple of other examples, which, just frankly don't do better than the standard React pattern, so I'm not going to discuss them. And then finally, when you look at OpenAgent, which is the results that they came up with, you do see a very marked improvement, like a very marked improvement. You're getting almost 2x what you'd get with React in answering these questions, mostly because some of these domains, like let's take a look here, computer vision problems, being able to call tools so that a language model can do, reasoning on computer vision tasks, it makes sense you're going to get this giant improvement. Bioinformatics tasks, you get an insane 4x improvement here. So this doesn't apply across the board. You can see that, interestingly, for chemistry, you don't get this change as much. For finance, you do. My hypothesis is that you see these boosts as a function of how well the GitHub community, which is what's providing the tools, how well the coverage is for each of the domains that are specified up here. So put in another way, I bet there's not a lot of phenomenal GitHub repositories to solve advanced chemistry problems, but there are some great repositories for bioinformatics problems, for computer vision problems, and perhaps even for security analysis problems. And that's the reason why for those, naturally, we're going to see that OpenAgent, who has access to those GitHub repositories, gets this large boost. So friends, that's it for today's lecture. I will see you all in the next video.